Hello guys, welcome to our today's lesson. This is Kamiti. Now, we are still analyzing simple stresses and strains, and we got a question here that says the bar shown in the figure below is subjected to a tensile load of 50 kilonewtons. So you have a load of 50 kilonewtons that is trying to stretch this member. Find the diameter of the middle portion. This is the middle portion. We have to find its diameter. If the stress in this middle portion is limited to 130 meganewtons per square meter. We are also to find the length of the middle portion, that is x. If the elongation of the bar is 0.15 millimeters, take Young's modulus of elasticity to be 200 giganewtons per square meter. Now, let's begin with determining the diameter of this middle portion. And since we are given the stress, we know very well that stress is given by load divided by cross-sectional area. Let's make area the subject of the formula. So the area will be given by load divided by stress. In this case, the tensile load is 50 kilonewtons. So let's convert it to newtons. We multiply it by 1000 since 1 kilonewton is equivalent to 1000 newtons. Then we divide this by this stress, the stress in the middle portion, that is 130 meganewtons per square meter. We convert it to newtons per square meter. Since 1 meganewton is equivalent to 1 million newtons, I mean. Now, when you divide 50,000 divided by 130 times 10 raised to power 6, you are going to get an area of 3.846 times 10 raised to the power of -4 square meters. So this is the cross-sectional area of the middle portion. And remember, since we are talking about diameter, it means that the cross-section is a circle. Now, area of a circular section is given by pi over 4d squared. We need the value of the diameter, so we make diameter the subject. And in this case, the diameter will be given by the square root of 4a, divide this by pi. So 4a divided by pi. So in this case, we are going to have 4 multiplied by cross-sectional area of this middle section, which is 3.846 times 10 raised to the power of -4. Then we divide this by pi, and then we find the square root of that. And in this case, when you do so, you are going to get, in this case, when you do that, you are going to get the diameter of the member being equal to 0.0221 meters. So that is the diameter of the middle portion. Now, when we convert these units from meters to millimeters, that is multiply this by 1000, since 1 meter is equivalent to 1000 millimeters, we are going to get a diameter of 22.1 millimeters. 22.1 millimeters, that is the diameter of the middle portion. So we have answered the first part of the question. The second part of the question is asking us to determine the length of the middle portion. Now, we know this, that there are these relations. Young's modulus is given by the ratio of stress to strain. Stress is given by rod divided by cross-sectional area. On the other hand, strain is given by change in length, or the elongation or the extension, divided by the original length. So when we substitute the stresses with their formulas in the Young's modulus, we are going to have Young's modulus of elasticity will be stress, which is load over area, divided by strain, which is change in length divided by the original length. And this is going to give us load over area times length divided by the change in length, that is reciprocal. Therefore, Young's modulus of elasticity will be given by load times length divided by cross-sectional area times change in length. Now, in this case, we are going to make change in length the subject. Since when you look at this point here, we are given the elongation of the member. So already we have the elongation of the member. And therefore, when we make change in length the subject, we are going to have change in length is equals load times length divided by cross-sectional area times the Young's modulus of elasticity. Now, in this case, since the end portions have got equal cross-sections, since their diameters are the same, we are going to say this. The total elongation of this member or this bar, total elongation or extension, will be given by the extension of the end portions. Extension of the end portions. Then we add to extension or elongation of the middle portion. Extension of the middle portion. Good. Now, we have the formula of change in length or extension in this case. Now, when we start with the elongation or extension in the end portions, we are going to have this. The elongation in the end portion will be given by the load multiplied by the length of the end portions divided by the cross-sectional area of the end portions. Cross-sectional area of the end portions times the Young's modulus of elasticity of the bar. Now let's determine, in other words, we are going to determine the area of the end portions. Then we are going to add these two, load times the length of the middle portion divided by cross-sectional area of the middle portion times the Young's modulus of elasticity of the member. Now, let's determine the area of the end portions. Now, the area of the end portions will be given by pi over 4d squared. And in this case, this is going to be pi over 4 times diameter of the end portion, 40 millimeters. We convert that to millimeters. We divide 40 by 1,000. 1 meter is equivalent to 1,000 millimeters. And when you divide 40 by 1,000, that's going to be 0.04. We square that. And this is going to give us an area of 1.2566 times 10 raised to the power of -3 square meters. So that is the area of the end portions. Let's determine the stress of the end portions. Now, if we take this P over A, we are going to get stress. Therefore, we can say this, we can extend this, we can rewrite this relation as follows. The stress of the end portions times the length of the end portion divided by the Young's modulus of elasticity. Since P over A is equals stress, then we are going to remain with L over E, which is there. Then we add these two, stress of the middle portion plus, that is times the length of the middle portion, divide this by the Young's modulus of elasticity. So let's determine the stress of the end portions by taking the load divided by the cross-sectional area of the end portions. Therefore, the stress of the end portions will be given by load, which is 50 kilonewtons. We convert to newtons by multiplying 50 kilonewtons by 1,000. Then we divide this by cross-sectional area of the end portion, which is 1.2566 times 10 raised to the power of -3. And when we do so, we are going to get a stress of 39.79 times 10 raised to the power of 6 newtons per square meter. So that is the stress of the end portions. From there, we are going to determine the area of the middle portion since we have the diameter. We have the diameter of the middle portion. Therefore, the area of the middle portion, the cross-sectional area, will be pi over 4d squared. The diameter is 0.0221 meters. So we are going to work with meters. 0.0221, then we square that. And when we do so, we are going to get an area of 3.836 times 10 raised to the power of -4 square meters. So that is the area of the middle portion. We had already been given the stress in the middle portion. That is stress in the middle portion is 130 meganewtons per square meter. When you write that into newtons per square meter, we are going to have 130 times 10 raised to the power of 6 newtons per square meter. Awesome. Then we come back here and apply this formula. So we are going to have the stress in the end portion, which is 39.79 times 10 raised to the power of 6 multiplied by the length of the end portions. In this case, the middle portion have got a length of x, then the entire bar have got a length of 250. Therefore, when we subtract x from this 250, we are going to get the length of these two end portions. So this is going to be 250 minus x. So that is the length of the end portions. Then we divide this by the Young's modulus of elasticity of the bar, 200 giganewtons per square meter. We convert that to newtons per square meter by multiplying by 10 raised to power 9. Remember, 1 giganewton is equivalent to 1 trillion, 1 billion. Yeah, a billion I've got 9 zeros. So 10 raised to the power of 9. Plus the stress in the middle portion is 130 times 10 raised to the power of 6 times the length of the middle portion, that is x. Right. This one is not 250 millimeters. We must convert it to meters. We are working with meters, by the way. So 250 divided by 1,000, that becomes 0.25. Sorry for that small error. So 130 times 10 raised to power 6 multiplied by x, the length of the middle portion. Then we are going to divide this by the Young's modulus of elasticity, 200 times 10 raised to the power of 9. This one will be equal to the total elongation of the bar, which in this case we are being told is 0.15 millimeters. We got to convert this to meters. Therefore, we are going to do what? We are going to divide this by 1,000 so that we can convert it to meters. So when you divide that by 1,000, you are going to get 1.5 times 10 raised to the power of -4 meters. Now what we are going to do, we are going to multiply through by 200 times 10 raised to power 9. Definitely here it will cancel, here it will cancel. So we are going to have 39.79 times 10 raised to the power of 6 times bracket 0.25 minus x plus 130 times 10 raised to the power of 6 times x is equals 200 times 10 raised to power 9 times 1.5 times 10 raised to the power of -4. Then to make work easier, we are going to divide both sides, or we are going to divide through by 39.79 times 10 raised to the power of 6. Definitely when we do so here, we are going to remain with 0.25 minus x plus, when we divide 130 times 10 raised to power 6 divided by 39.79, that is going to give us 3.267x. Then this one will be equal to 200 times 10 raised to the power of 9 times 1.5 times 10 raised to the power of -4 divided by 39.79 times 10 raised to the power of 6. That is going to give us 0.754. 0.754. Then we are going to have negative x plus 3.267. That is going to be 2.267x being equal to 0.754. We take 0.250 the other side of the equal sign. That's going to be minus 0.25. So we are going to have 2.267x is equals 0.754 minus 0.250. That is going to be 0.504. Then to get the value of x, divide both sides by 2.267. This side again divide by 2.267. And when we do so, we are going to get the value of x being 0.222 meters. 0.222 meters. Now, since the entire length of the bar is given in millimeters, we are going to give the length of the middle section in millimeters as well. So multiply this by 1000. And therefore, the length of the middle portion will be 222 millimeters. 222 millimeters. So, ladies and gentlemen, that's how we go about. So, we appreciate so much for watching our video. Please do subscribe if you haven't. Thank you. Let's meet in yet another lesson.